Hello, everyone. Good morning. Well, for me, good morning. For you, by the time you get this, it will be good afternoon. Welcome to Chemical Engineering 374 Online. Today we'll be talking about dimensional analysis. Remember, last time we talked about mechanical energy and friction and how to deal with the problems that include non-idealities. Next, we're going to get into friction and how to calculate it. But before we get there, it's important for us to introduce a new tool. This tool will be strange, it will be unfamiliar to you, and a little different, but ultimately it will be very helpful both in this class and as you do your research and learn how to do experiments for determining the best way to evaluate a system that you don't know a lot about. And we call that tool dimensional analysis. Hope you prayed already. If not, TAs, take a pause and pray. Otherwise, we'll go ahead with the spiritual thought. This is from just this last conference, which, by the way, was awesome. It's from President Monson, and in his Sunday morning address, he said, "It is not enough, however, merely to believe in him and his mission. We need to repent, to work and learn and search and pray. Repent and improve." How grateful I am that we have a knowledge of our Savior Jesus Christ, and even more so, that we have prophets and apostles who speak to us. Interesting to me that over the weekend, the very heavy focus was not on the law of Mosaic application of the commandments we've been given. Rather, almost the entirety of the focus of conference was how to go beyond that, how to seek to build a relationship with our Savior once we're obeying the commandments, and how to improve that relationship, how to learn of him and believe in him, and therefore become like him. And I thought that was very succinctly summarized by the words of our prophet, President Thomas S. Monson. So my hope is that we will take his counsel to heart, myself included, to be able to improve, to search and pray, and to repent daily. So here's the roadmap. As you guys are familiar with, we've covered fluid properties, we've covered non-moving fluids or statics, and now we're right in the thick of the integral analysis or the Eulerian analysis. And right now we're down about ready to move into fluid system analysis, but before we do, we should cover dimensional analysis. Key points for today, we're going to talk about the motivation for doing dimensional analysis. We're going to talk about some of the theory and some of the limitations. We're going to talk about how to approach experiments. Primarily what we're interested for experiments is to learn some of the phenomena about a property, but we want to minimize the cost, maximize the practicality and efficiency, and develop really a qualitative understanding of the system, understand what factors impact our experiment. In order to do that, we're going to introduce dimensionless groups. By using dimensionless groups, we can minimize the cost and maximize the practicality and efficiency of our experimental system. And when we do dimensionless groups, pay attention to the process. What we're going to do is we're going to eliminate the units. We're going to cover 3 different methods. 1 starting from governing equations, 2 is using force ratios, and 3 is using something called the pi method. And we're going to go over a couple examples, and then we'll talk about similarity and scale models. So, as an example for our introducing this tool for addressing experiments and learning about a system, we're going to talk about an example that we're already somewhat familiar with, and that is, pipe in a flow. We're going to do lots and lots of pipe flow as an engineer and specifically in this class. So far, what we've covered is the Bernoulli equation, which is primarily frictionless flow. We did introduce how to do friction last time, but we just introduced that fudge factor F. What we want to know is how to actually evaluate quantitatively the friction in a pipe. We're going to do that at the end of this week and beginning of next week. But we have actually done it before. We looked at friction, or the shear force, on a plate using Newton's law and viscosity. Here, hopefully you remember this. Now note I did neglect the minus sign. Whoops, I will put that in for the notes themselves. And what we did is we balanced the forces for this plate. So we're going to do that again. This time we're going to consider a pipe, and we're going to balance the forces acting on this little section of pipe. And really we have two forces. We have the pressure forces, one on each side, pressure 1 times area here, pressure 2 times area here, and then we have the shear force, which is tau, or the shear stress, times the area, which is the surface area, which is pi d, or the circumference, times the length. Okay? And what we want to do is figure out how we can determine friction based on this force balance. We're going to go into details Friday about this. But for now, let's try and say something qualitative about it if we can. First of all, remember last time we talked a little bit about turbulent versus laminar flow. Well, almost all flows are turbulent. And since there's so many complicated patterns in turbulent flow, instead of just trying to determine what the flow is specifically at each point, what we do is we consider the averages of the flow. And that's where we end up getting this nice parabolic flow rate, is the averages of all the turbulent flows. So how do we characterize pipe flow? Well, I mentioned that almost all flow is turbulent. Turbulent flow is complex and random and chaotic, and it's difficult to measure, so we're going to consider averages of the flow. So how do we measure and relate the important properties to determine what the friction losses are? So let's list the variables that are important. The velocity of the flow is important. The pressure drop is important. The length of the pipe is important. The diameter of the pipe is important. The viscosity of the fluid is important. And the density is important. Where did we get these things? Well, we know some of these things in terms of delta P and rho were important based on the Bernoulli equation. Delta P is what we're looking for. L is the length, which we know is part of the shear stress equation. Viscosity is also a part of the shear stress, as is the velocity. That's a part of the shear stress. And then finally, the areas are important, but it's the same in both cases, so we can cancel it out. Well, this gives us 6 terms that are important, but let's say we didn't know how long the pipe was, or we wanted to look at the pipe regardless of the length. We wanted to not have length be part of our evaluation. So then what we're going to do is we're going to combine the terms, and we're going to come up with one term called delta P over L, or in other words, the unit, the pressure drop per unit length. And so now we have 5 different parameters that we know are important for evaluating friction, but we don't know exactly how. Now, before we go on, I want to demonstrate what we mean by laminar versus turbulent flow. This is an experiment demonstrating that. Whoops. You can see here that the flow is starting out laminar. Nice, smooth streamlines, very low flow, and that line of red dye starts out constant. Well, as the speed starts to increase, there begins to be slight little oscillations. You can see the oscillations in that dye. It's starting to have a little more perturbations in the axial flow, which you can see by those loops coming down. Sorry, their camera skills aren't great. I pulled this off of YouTube. And what they're going to do is they're going to slowly increase the speed of this flow. And you'll see that as the speed increases, the perturbations or the nonlinear flows begins to increase. There begins to be vortices and swirling inside this. And it's gradually increasing from a transition region into a more turbulent zone. And now you can see that it's turbulent. You're actually starting to fully disperse this dye because there are vortices and transversal flows that actually cause mixing of this dye. So it's no longer in a nice smooth line. Rather, it is becoming a fully turbulent flow. Okay, I'm going to show one more example here. This is taken from a company website. And this is illustrating flow at the same speed, but on the left, the bubbles in the flow, you notice, are moving in a nice smooth line. On the right, there's a helical wire on the inside that causes disruption of the flow lines and jumps it into the turbulent regime. This time it's not velocity that does it, but something else entirely. And you can see highlighting with the light behind it that the laminar flow on the left is nice, smooth, continuous flow lines, where on the right it's much more rough and vigorous mixing is involved. So this is a great example of laminar, which is on the left, versus turbulent, which is on the right, flows. We'll talk about what causes turbulent flow very shortly. But in the meantime, just recognize that it's not just velocity that changes turbulent to laminar, but the flow pattern can also, the geometry can also impact the flow pattern, which will change it from a strictly laminar to a turbulent flow regime. Okay? So, how could we determine some kind of relationship between the unit or the pressure drop per unit length and these other parameters? Well, the first thing we could do is solve the governing equations. You guys know what the governing equation for flow in a pipe is? Well, if we want to know the pressure drop per length, we've got to know what the pressure is at every single point. Which method is that, Eulerian or Lagrangian? That's right, it's Lagrangian, which means we've got to solve the Navier-Stokes equations. Not so fun, is it? You can do it, but it's complicated, and it takes a lot of time. Or in other words, we call that computationally expensive. It could take you an entire month just to try and do the numerical analysis of these systems by hand, depending on the conditions of your pipe. So that's not what we always want to jump straight to. It can be done, but it's expensive. Another route, could we do experiments? Of course, but a few caveats. If we're doing an experiment, we need to figure out what the design parameters are. How are we going to build this thing, and what is the range of phenomena that we're going to cover? In other words, we want to span the space. Let's say we wanted to look at the behavior of water, and we decided that we wanted to run an experiment heating water from 10 degrees Fahrenheit all the way up to about 90 degrees Fahrenheit. Well, what does that mean? That means the water is liquid during the entirety of the experiment. And if we did not understand the properties of water, and we were to run that experiment, our conclusion, which we would erroneously come to, would be that water is liquid under all conditions because we didn't span the entire space. To do that correctly, we should start maybe at minus 10 degrees Fahrenheit and move all the way up to 120 degrees Fahrenheit so that we could see what those parameters were. In fact, we should probably go even higher than that and go to 212 degrees Fahrenheit since that is the point at which water boils. Okay? So you want to make sure that your experiment spans the entire space of phenomenon. If we're looking at pressure drops, we don't want to find out after the fact that there was actually a precipitous drop-off where at a certain speed the pressure drop jumped to be astronomically high. That's an important thing to know. So when we're setting up an experiment, we need to make sure that we're doing an appropriate range of variables that spans the entire space of interest. The next question is, how many experiments should we do? Let's say we're trying to measure the pressure drop per unit length. And we know that the diameter of the pipe, the velocity, the viscosity, and the density of the fluid all have an impact. So let's say we were going to measure just 10 points for each of those different variables. Well, for each variable that we measured, we'd have to measure the variance with respect to other parameters. So let's say we wanted to do diameter. So let's say we're going to go from 1 to 10 inches in 1 inch increments. Well, we start with 1 inch, and then we have to pick a velocity, a viscosity, and a density, and then we have to cycle through all of those variables for each 1 inch diameter experiment. That means we have 10 to the 4th experiments, or 10,000 experiments to do. That is a ridiculously huge amount of experiments. We don't want to do that. So let's be smart and be efficient. Let's come up with a way where we don't have to do explicitly every single measurement. Rather, we'll try and come up with a way to find interdependencies of the variables just by doing a quick analysis up front. And that's where dimensional analysis comes in. Dimensional analysis is a tool that lets us learn something about a system without explicitly modeling and experimenting with every single aspect of that system. It's a very powerful tool. What it does is that actually gives us insight into the equations. Next time I will demonstrate and show you how, without knowing any of the mechanics or the theory behind heat and mass transfer, we can actually use dimensional analysis to figure out some pretty important things about cooking a roast. Okay, so it gives us insight. It also shows us how these different parameters are related. Finally, perhaps most importantly, it will reduce the number of parameters in a system. So instead of having the diameter, the velocity, the viscosity, the density of the pipe flow, we can reduce those by combining those into different groups, or what we call dimensionless numbers, and then we'll only have 1 or 2 groups to model rather than 5. Another thing that this does is this allows us to come up with something called scaling laws. When we do an experiment, oftentimes we don't want to do it full size because then it's much more expensive and much more difficult to manage. So what we end up doing is we end up developing what we call scaling laws, or starting with a small experiment and then scaling that up so it's similar to the large experiment. Okay? So now just a brief discussion. When we talk about units, nature doesn't recognize our units. All that nature recognizes is the fundamental parameters. It recognizes a length. It recognizes a mass. It recognizes an energy. But it doesn't know anything about seconds or hours, doesn't know anything about electron volts versus joules or kilograms versus pounds. That is our, or mankind's, attempt to characterize and understand fundamental parameters. Okay? What nature understands well is relative sizes. For example, it understands well that an elephant is 10 times larger than a horse, for example. I don't know if that's really true, but that's the kind of relative comparisons that nature understands. Or, for example, a praying mantis is 100 times larger than a fly. Those kinds of comparisons are the ones that we see in the natural world. When we use the lengths and meters or inches to do those same analyses, or the masses, pounds versus kilograms, we put our own interpretation into that. Okay? So that may not make a lot of sense. Hopefully it will become more clear the rest of today and also tomorrow when we discuss this. Finally, going back to this pipe flow, when we do an experiment or we're looking at phenomena, an important thing to recognize is that not all parameters are independent. Back to that pipe flow example, let's say we had a flow with a velocity of 4 meters per second and the diameter is 1 meter. Okay? If we were to now say that we were going to reduce the flow to 2 and decrease the diameter by the square root of 2, we will end up having the same phenomenon. Okay? The flow rate is going to be exactly the same when it's got a smaller velocity and a smaller diameter in the ways indicated. Right? If you don't believe me, try recognizing that it's going to be pi times d over 2 squared times velocity. That gives you the volumetric flow rate. And it's the same for both of those circumstances. That means that the volumetric flow rate is not independent because you have, it's not, the velocity and the diameter are not independent because the volumetric flow rate is going to be the same even if you adjust those differently. Okay? Alternatively, a flow with a viscosity of 20 and a density of 1.2 is the exact same as the flow with viscosity equals 40 and density equals 2.4. That one is a little less clear. We haven't gone through the analysis of flow rates there. But basically, the key is not all parameters are independent. You might get some that are coupled, whereby adjusting one or the other or both, you can get the same value for flow rate for both values of that parameter. So what we're trying to do in dimensional analysis is we're trying to find 3 independent parameters, which usually are a combination of the different variables. Okay, we call these the dimensionless groups. And there's 3 ways to do this, and I'm going to go over each, and hopefully the examples will make it more clear, because just talking about it is a little difficult to grasp. So first we're going to talk about governing equations, then we're going to talk about using force ratios, and then we'll use the method that's described in your book that's a lot more common, and that is the pi method. Okay? So from the governing equations, what we do is we start with the equation we know drives the phenomenon or describes the phenomenon. So in this case, we know for flows where mechanical energy is conserved, density is constant, etc., all those 6 assumptions, the Bernoulli equation in other words, we know that this describes flow of a fluid. So if we want to determine dimensionless numbers, what we would do is divide all the other terms by one of the terms that we have. In this case, let's arbitrarily pick velocity squared over 2. If we were to divide all the other terms by velocity squared over 2, we would end up with a pressure term, 1, a height-related term, and the constant divided by v squared over 2. Well, what's unique about each of these terms? They all are dimensionless. And it turns out this is a very, very significant and well-known number, the coefficient of pressure. This is related to a well-known number called the Froude number, divided by 2, or 2 divided by the Froude number. Okay, so we've come up with dimensionless numbers that help us understand the flow. More importantly, these are independent parameters. So if we know the governing equation, we can come up with the dimensionless numbers by simply dividing the other factors of that governing equation by one of the coefficients and factors. Another idea is to use force ratios. So we'll take the most important forces in a problem and form ratios with them. As an example, again with the Bernoulli equation, we have the pressure term, the gravity term, the momentum term, or in other words, the velocity term, and these are also the forces. So if we evaluate the forces, we can have the pressure force, the gravity force, and the momentum force. And we can use these forces to make ratios, and we will come up with the same parameters once we take ratios as we had in the previous example. Okay? Last approach is what we call the pi method. This is a more systematic approach. For the force ratios and the governing equations, there's 2 challenges. One, you have to know a lot about the system. You have to understand the forces. You have to know governing equations or something like that. 2, it requires a lot of intuition and experience. Well, the pi method is a much more general and systematic approach. It's described in the book, and it's the approach that for the homework today, I would like you to use in order to learn how to develop these dimensionless numbers. It'll take some practice, but that's what we have homework for. Feel free to work with your peers in order to make this happen. And again, if you have questions, send me an email and let me know. This is a fairly simple approach, but there's lots of conditions and rules that you need to follow in order for it to be generally applicable to all circumstances. Also, a warning, your book is a little bit confusing here. So be aware of that. And again, if you have questions, feel free to ask the TAs directly or send me an email and I'll get back to you as soon as I can. So let's use this pi method to evaluate pressure drop in a pipe, just like we were looking at for the other methods. First step is we want to list all the parameters and variables associated with this problem. Additionally, we want to list their symbols and their units. So in this case, we're looking at the unit pressure, or pressure drop per unit length, which is delta P over L, and we list the units for it. We also want to know the diameter of the pipe, which is D, and the units are meters. We do the same thing for all the others, density, viscosity, and velocity. Those are our 5 parameters, remember, that we knew were significant. Okay? So when we look at this, the total number of variables, n, is 5. There are 5 variables associated with this problem. The next step, what we do is we count the number of dimensions. This is not units, because remember, units are arbitrary. They're things that we apply to nature to try and understand them. But the fundamental dimensions are set. So in this case, it would be weight, length, and time. Those are the fundamental parameters. So how many fundamental dimensions or parameters are there in this problem? There are 3. We have weight, illustrated in 3 of these terms, here, here, and here. We have the length, mm, and we have the time illustrated by the seconds. Once we know the number of dimensions, we can figure out the number of dimensionless independent pi groups, or in other words, k sub pi, and that's equal to the total number of variables minus the dimensions. In this case, there are 2 pi groups. Generally, one of those pi groups is the dependent pi group, or in other words, the one that corresponds to the quantity we're trying to find. So in this case, we're trying to find delta p over L. So what we can know is that one of the pi groups will involve a delta p over L because it will be the dimensionless group we're solving for. The other one is the independent pi group, and that's the one that we can adjust to determine how that changes our delta p over L. Okay? So we need 2 pi groups in order to account for the variance of units or parameters or dimensions compared to the number of variables that we have. Okay? So now the next thing is to find the pi groups. When we do this, we have to make sure that every variable is included in the pi groups. Okay? The pi's need to be independent. Usually we can find the pi's by trial and error, but we can set up an equation, an algebraic equation, where we list the exponents for every unit and solve for the value of exponents that will eliminate this. Okay? And this requires a little bit of experience and a little bit of basic common sense. For example, if we want to find a relationship for delta p, then we don't want delta p in all the pi groups, because then it's going to be difficult to try and solve for delta p. I'll show you what we mean. So let's do an example. Here we have those same variables that I listed before, and we want to find the pi group. So we're going to start with delta p over L and try and get rid of the units by using all the other variables. So here, delta p over L has units of kilograms per meter squared per second. Well, let's say, just by intuition, we're trying to get rid of the kilograms and we have some meters on the bottom. That looks almost like density. So let's try dividing by the density. So now we have delta p over rho times L, and we end up getting the units of meters per second squared. Well, let's see. Without reintroducing a weight, the next thing we could do maybe looks like velocity, because it also has meters and seconds. The seconds is squared, so let's divide by velocity squared. Once we do that, we fully eliminate the seconds, and we end up getting delta p over rho v squared L is equal to, now the units are 1 over length. So next we have the diameter. And the diameter has units of length, so we just multiply it by the diameter, and we end up getting the diameter times delta p divided by rho v squared L. This turns out to be extremely important, and part of our evaluation for friction has exactly this term. This is the first dimensionless number, or the first pi group. It's a dimensionless number, and it shows the independent parameters, or the parameters that if this changes, it will not be similar to changing the other pi groups. You won't get the same result for changing multiples of these independent groups because they are independent. So now let's try the second one. Just based on experience, we'll start with the viscosity. The units here are kilogram per meter second. So we'll divide by density. Same method I'm thinking as before. This time it's viscosity divided by density. We get meters squared per second. So this time let's divide by velocity, since the second is not squared. We end up getting viscosity over rho v. Now the unit left is meters, so let's divide by d. We end up getting mu over rho v d. Well, it turns out that these are non-dimensional pi groups. We now have our 2 pi groups. In other words, what this is saying is if we're looking at the pressure loss as it's associated in this group of variables is going to be dependent upon how these variables change. So instead of having 5 different parameters we're trying to adjust, we can now just adjust this single parameter. And if we adjust this single parameter, we'll get a single one-to-one function that describes how these two are correlated. Okay? So in this case, the pi groups are non-dimensional, so they're not unique. For example, if you were to square this whole term here, that would also be a pi group. It has the same connections as this one, or the same interrelations between variables, but it is also a valid pi group. So keep in mind they're not unique. You might not get the same answer as somebody else, but it is still a valid pi group. Okay? In other words, pi 2 could be a product of pi 1 and 2. In other words, you could replace 2 with 1 times 2, and it would still be a valid pi group. In other words, it would still be dimensionless and describe the system. Okay? As I mentioned earlier, you can take any pi group to any power, and that's okay. In fact, if we take the negative power of that second number here, we end up getting the Reynolds number, a very well-known dimensionless number that we will be using forevermore in fluid mechanics because it helps us to understand flow regimes like turbulent versus laminar. This group here is also important. I labeled that wrong. It's pi 1, not pi 2. But pi 1 is also important because it directly describes pressure drop as a function of these other variables. We'll use that a lot more when we do the laminar flow in a pipe. Okay, so in this case, we found pi groups just by visual inspection, which is reasonably easy. The book teaches you the repeating variables approach and gives a lot of rules that you have to follow in order to make it work. If you prefer the methodological approach to doing this rather than trying to rely on experience and just kind of visual inspection, then this is what you'll do. You'll pick a number of repeating variables, j, which in this case is the number of dimensions, that will show up in all the pi groups. So in this case, we want delta p. We won't pick delta p as a repeating variable. So we'll arbitrarily pick delta p as a non-repeating variable. And let's pick, again, just as in the last approach, let's pick the viscosity as a non-repeating variable. That means the other three variables, d, rho, and v, are going to be our repeating variables. Then what we're going to do is by forming the two pi's using the leftover variables, one variable for each pi. Okay, so in this case, delta p and u are going to be the leftover variables. So to find the first pi group, we take our leftover variable, delta p over L, and we're going to have the other three repeating variables be a part of it to some power, which we don't know yet, a, b, c. And we're going to set up an algebraic equation so that the parameters or the values of a, b, and c will make the units of d, rho, and v exactly opposite or inverse of delta p over L. What that does is it will make them completely dimensionless. So here, kilogram per meter squared per second squared, which is the units of this term, times length to some exponent, kilogram to some exponent, and mass to minus 3 of some exponent. I'm sorry, that should be, whew. So anyways, A and B are both together, and C has these units, meter squared per second squared. Kilogram is mass per meter cubed. So some mass to the A, or I'm sorry, some length to the A represents D. Some kilogram per meter cubed to the B represents your density term. And your meters per second to the C is your third term. And then you literally just solve an equation for A, B, and C, where in this first term, kilogram is the first power. So B should be minus 1. You set up a series of equations in order to solve this. So kilograms, 1 from the pressure term, plus B, that should be 0 because we want it to be dimensionless. So we simply solve. We do the same thing. Now let's do C, or velocity. Okay. We have meters squared per second squared. And so minus 2 minus C should also be 0. And so we solve there and find that C is equal to minus 2. And then we do the same thing plugging that into B. We're literally just using the exponents as an algebraic expression to do the same thing that we did here where we visually inspected and decided what to multiply and divide by. But here there was a methodological approach to do that. Okay? Let's go back to the Reynolds number. So the Reynolds number we're going to be using all the time. In fact, the Reynolds number is the number used to determine whether a flow is laminar or turbulent. Okay. Generally, these dimensionless numbers, like the Reynolds number, represent the ratio of two physical phenomena. In this case, that ratio is the inertial versus the viscous forces. Okay, remember viscosity is a function of the shear stress is a function of the viscosity, and the viscous forces are related to the viscosity of a fluid. The inertial forces represents the inertia of the fluid itself. So if we take the ratio of the inertial forces to the viscous forces, we end up with the Reynolds number. And this is the most important number in fluid mechanics. It's used to define friction. It's used to define flow regime. We will use it all the time. It was actually developed by a guy named Osborne Reynolds, lived in the 1842 to 1912. He was a British engineer, and he was a very important pioneer in terms of developing fluid mechanic mechanisms. So this Reynolds number was developed by Osborne as he studied pipe flow, particularly in turbulent versus laminar regimes, and determining the transition between the two. So we're going to talk about the Reynolds number a lot. I would definitely, absolutely, and unequivocally memorize the Reynolds number, understand that it's the ratio of inertial to viscous forces, and know how to calculate it for any given set. That is absolutely vital. So please make sure that you understand and know the Reynolds number. Once we do that, then we can use these dimensionless groups for something called similarity. If we're trying to compare something large to something small, for example, if we were to compare an average-sized man here to a Goliath-sized man, we want to do an analysis to make sure that we're comparing them appropriately. In other words, if we want to do an experiment on this little guy and have it correspond accurately to the big guy, we need to use something called scaling laws. And scaling laws are derived from the dimensionless numbers. You'll need to know this for your homework. In order to correlate a scale model to a full model, what you need to do is you need to come up with a relationship or a dimensionless number for the one, and so long as that dimensionless number is the same for the larger group, then the phenomenon will be the same. Okay? In other words, let's say you were trying to figure out the pressure drop of blood through a main artery in the little man. Well, the big man, that artery is going to have a bigger diameter. But if you adjust the Reynolds number, in other words, you use a fluid that has a viscosity that's half as large, or if you were to do a shorter length, but have the same Reynolds number, so some factor in the Reynolds number to correspond for the larger diameter, so that the Reynolds number was the same, you will have exactly the same flow phenomenon between the blood vessels of the larger and smaller group. That's what we mean by scaling laws and similarity. We need to have the dimensionless group remain the same to two different sizes, and that will describe the same phenomenon. Okay? Using that, we can determine things. For example, we can determine why animals and bugs grow to the size and shape that they do. In other words, when you apply non-dimensional analysis, it turns out that there's some factor that grows out of control if the bug or the animal gets too large, and that in essence limits the size that these animals can get to. Okay? So talking about similarity, as chemical engineers, we will regularly design or analyze processes in chemical plants or oil plants or whatever. What we do is we'll use the governing equations, but these equations are often inadequate. Either they're too complicated to solve, or they don't adequately describe the circumstance, or maybe we don't have all the equations we need for the system. To make things worse, reality is often far more complex than our nice little problems. Remember the open-ended problems we've done with Spanky, for example. He'd have to have the hose exactly in the right direction at all times. Otherwise, you're going to start to have an acceleration force from side to side. In other words, it's no longer a 1D problem. That means reality, which is often the case, is far more complex. And because of that, we can't really adequately solve it using the governing equations. It is too complicated or computationally expensive. So what we want to do often is do experiments where we will model reality using a small scale experiment. The cost is high, which is why we start small, and once we feel like we understand well the phenomenon, then we can scale up to a larger system that more accurately resembles the system we're trying to design. But we have to make sure that the small and the large scale are consistent. In other words, as has been said before, we want to have our failures on a small scale in private and our successes on a large scale in public. So there's 3 requirements for similarity so that anything we do on a small scale correlates to something on a large scale. And that is 1, we need to have geometric similarity, or in other words, the shape needs to be the same. 2, we need to have kinematic similarity, or in other words, the velocities need to be the same. And 3rd, we need to have dynamic similarity, or in other words, the forces need to be similar. Once we satisfy these groups in our basic design, then we can find the dimensionless groups and make sure they're the same for the model and the scaled up versions. Okay? Dimensionless groups don't need the full model, they just need the import parameters. You'll know that you don't have all the dimensionless groups if you're doing homework or a research project because you will not get the right number of independent pi groups. That means you need to either add another variable or take away some phenomenon that isn't important to the model. This is a lot to digest. That ends our lecture. I recognize there's a lot here. Again, please go see the TAs or call me or email me, more likely, since I'll be in meetings, to get help. And I will try and help in whatever way possible. In this case, the homework will help. Please give it an honest shot on your own to try and understand it. You can work in groups, but I would recommend that you take the extra effort for this lesson to understand what's being done and said and what the rules are. Use the book as a reference if you have to. Really try and understand these dimensionless numbers, dimensional analysis, and scaling similarity laws, because they will be important for our work moving forward. Thanks, guys. Hope you have a great afternoon, and we'll talk to you later. Bye.